Εγώ είμαι πάνω στην μπουκαπόρτα εκεί πέρα.
Όχι.
Νομίζω αυτό.
Κύριε Πρίτανη, κύριοι καθηγητές, κυρίες και κύριοι, σας καλωσορίζουμε στην τελετή αναγόρευσης του καθηγητή Leymann, σε επίτιμο διδάκτορα του Τμήματος Επιστήμης Υπολογιστών του Πανεπιστημίου Κρήτης. Προσφώνηση από τον Πρίτανη του Πανεπιστημίου Κρήτης, καθηγητή Επιτήρη Στεφάνου.
Λοιπόν, καλησπέρα σας. Όπως συνηθίζετε, θα αρχίζω λέγοντας λίγες λέξεις στα ελληνικά, μετά προς τιμή του καλεσμένου μας θα μιλήσω στα αγγλικά. Στη σημερινή τελετή υπάρχει ένας μεγάλος απόν, είναι ο Χρήστος Νικολάου. Παρόλο που η τελετή αυτή έχει ως στόχο να τιμήσει τον καθηγητή Leymann, είναι και μία τελετή προς τιμή της μνήμης του Χρήστου Νικολάου. Θα σας παρακαλούσα πολύ να σηκωθείτε να τηρήσουμε ενός λεπτού σιγή. On behalf of the community of the University of Crete, it is my pleasure to extend a very warm welcome to Dr. Leymann, Professor of the University of Stuttgart. Dear Professor Leymann, the academic community you are joining today is dedicated to excellence in research and teaching despite the hostile environment imposed by the state for Greek universities. However, dedication to science and permanent effort constitute our response to obstacles and challenges. Greek governments do not recognize our effort. However, the international academic community eloquently recognizes it. According to the 2014 Leiden University Classification for Research, the University of Crete in the field of natural science is ranked 5th in Europe and 43rd in the world above Imperial College. The University of Crete is ranked among the best 50 universities in the Times of Higher Education ranking of the world's best young universities under the age of 50. The ability of the university to maintain its position in this ranking for the 4th year running is a significant achievement in itself. It is a performance that reflects well on the academic community of Crete in the face of worsening recession conditions which have been impacting heavily on higher education institutions in Greece. Released on April 30, 2015, the results of the Times of Higher Education ranking coincided with the sudden loss of the computer science professor and former rector Christos Nicolaou. Christos would be particularly pleased with the fact that Crete has been ranked in this prestigious group of young higher education institutions every year since this ranking was first published in 2012. This result reflects the extroversive and research-intensive character of our university. Christos Nicolaou was the creative leader who worked hard to promote this vision common in our academic community. Since its foundation, our university established strict criteria for conferring the title of Doctor Honoris Causa. We recognize the outstanding achievements and contribution of individuals at the international level in physical and social science, medicine, literature, and arts. We also recognize academics, scientists, researchers, humanists, and scholars who have made a significant pioneering or revolutionary contribution in their field. In the past, we have conferred honorary degrees to Jorge Luis Borges, to Nobel laureates Jean-Marie Leymann and François Jacob, to cite some of them. Today, you are sharing this honor with them. Today, as the rector of the University of Crete, I am honored to confer to you, Professor Frank Leymann, the degree of Doctor Honoris Causa of the University of Crete with the honor and the privilege proper to it. Dear Frank Leymann, we are happy and proud that you share with us, by accepting this honor, our battle for academic and scientific excellence in this challenging era for Greece. We are honored also by your presence in this ceremony, which is a tribute to the memory of our beloved friend and colleague, Christos Nicolaou.
Thank you. Dear Professor Leymann, on behalf of our Dean, Professor Taroudakis, who was not able to attend this ceremony, it is my great pleasure to welcome you to our School of Science and Engineering. I would like to thank you for your presence. Your nomination not only enriches the Department of Computer Science, but all our faculty. I think it's very important for us to outreach and establish ties with outstanding scholars and renowned academic institutions. Thus, I would also like to thank the Department of Computer Science for this initiative to propose Professor Leymann as Honorary Doctor. I'm not a computer scientist, I'm a computational physicist. So I'm not an expert in your field of research to really appreciate it. However, considering the drive of our faculty to develop the science of computing in the computational sciences, and I looked at your web page, and I have the feeling that we can all greatly appreciate and profit from your scientific achievements, about which Professor Tsakalidis will tell us much more about. Thank you.
Προσφώνηση και παρουσίαση του έργου του τιμόμενου από τον πρόεδρο του Τμήματος Επιστήμης Υπολογιστών του Πανεπιστημίου Κρήτης, καθηγητή Παναγιώτη Τσακαλίδη.
Αξιότιμε κύριε Πρίτανη,
κυρίες και κύριοι συνάδελφοι, αγαπητοί φοιτητές. It is with great honor that today the Department of Computer Science of the University of Crete confers an honorary doctorate degree on Dr. Frank Leymann, a professor of computer science and the director of the Institute of Architecture of Application Systems at the University of Stuttgart, Germany. Professor Leymann is a pioneer in the fields of business process management, workflow management, service-oriented computing and architecture, web services, cloud computing, pattern languages, transaction processing, quality of services, and non-functional properties. For his sustained technological contributions to many of IBM's middleware products for 2 whole decades, Professor Leymann was appointed as an IBM Distinguished Engineer in 2000, and he was elected a member of the IBM Academy of Technology. Back in the early 80s, about the time that when Frank was starting his productive career at the Big Blue, a few thousand miles east, a brand new Department of Computer Science, the first of its kind in Greece, was inaugurated here in the island of Crete. The department was founded by people with a very clear vision to make this place known internationally for high-quality research in all areas of modern computer science, as well as for the high level of commitment to educating and building career opportunities on behalf of its students. Thanks to the vision and know-how of its founders, who understood the need to cut through the restraints of public bureaucracy, the innovative and youthful spirit of the University of Crete, and the fortuitous state of affairs, the department started with a clean slate, attracting high-caliber Greek scientists from abroad to fill early faculty positions. Among these young expatriates who left an established career in the technological mecca to return home was Christos Nicolaou, Frank's colleague and good friend at IBM. Back then, Christos was leading a research group at IBM's T.J. Watson Research Center in New York, introducing multiprocessor technology and load balancing in commercial transaction processing systems. Based on his research, performance and availability were dramatically increased for flagship IBM systems during the 80s and early 90s. As a result, Christos himself was awarded IBM Invention Achievement Award in 1992 and IBM's Outstanding Innovation Award in 1993. More or less a decade earlier than when Frank did, Christos also returned to Europe to try to distill the American industrious ways in science and technology into the infant CS department here in Crete. He soon did much more. He became the rector of the leading research university in Greece, spearheaded a major campus construction effort, and opened the university to international cooperation. Much because of his efforts, the University of Crete is now highly ranked in the list of the top universities in the world under the age of 50. Christos did a lot for this. He did his share to make sure that the original aspiration remained the same. He argued that this place needs to be extrovert, to always invite new people, to blend the new with the established, to try to be constantly renewed and retooled. And then, suddenly, a few days ago, he decided to say goodbye. Today is a day where we celebrate and we honor the presence of Professor Leymann, acknowledging his achievements in computer science with an honorary doctorate degree. Also, according to Frank's wishes, it is a day where we commemorate Christos, acknowledging his contributions to our university. So yes, it is a great pleasure that we have Professor Leymann with us. We are indeed honored, but at the same time quite desolate that his good colleague and friend is not among us, but rather watching from far away, somehow, hopefully feeling gratified with the thought that despite the harsh times, this place has come of age, very much due to his own efforts. Thank you.
Ανάγνωση του ψηφίσματος της αναγόρευσης και του διδακτορικού διπλώματος από τον πρόεδρο του Τμήματος Επιστήμης Υπολογιστών, καθηγητή Παναγιώτη Καναλίδη.
Το ψήφισμα, με την ομόφωνη απόφαση της συνέλευσης του Τμήματος Επιστήμης Υπολογιστών τη 17η Δεκεμβρίου του έτους 2013 και της Κοσμητείας της Σχολής Θετικών και Τεχνολογικών Επιστημών τη 16η Ιανουαρίου του έτους 2014, αναγορεύεται επίτιμος διδάκτορας ο Frank Leymann, καθηγητής του Πανεπιστημίου της Στουτγκάρδης, για την εξαιρετική συνολική επιστημονική του παρουσία και τη συμβολή στην πρόοδο της σύγχρονης επιστήμης υπολογιστών, στην ανάδειξη της διαχείρισης επιχειρηματικών διαδικασιών σε μια από τις βασικότερες λειτουργίες στη σύγχρονη βιομηχανία, στην ανάπτυξη τεχνολογιών υπηρεσιών κεντρικής αρχιτεκτονικής υπολογιστικών συστημάτων, στη δημιουργία διεθνών προτύπων υπηρεσίας διαδικτύου, στην ανάπτυξη τεχνολογιών υπολογιστικού νέφους. Το Τμήμα Επιστήμης Υπολογιστών και η Κοσμητεία της Σχολής Θετικών και Τεχνολογικών Επιστημών αποφάσισαν επίσης ομόφωνα να αναγράψουν με βράνη το παρόν ψήφισμα, το οποίο θα αναγνώσει ο πρόεδρος του Τμήματος Επιστήμης Υπολογιστών και θα επιδώσει στον τιμόμενο ο κοσμήτορας της Σχολής Θετικών και Τεχνολογικών Επιστημών. Αναγόρευση. Το Τμήμα Επιστήμης Υπολογιστών και η Κοσμητεία της Σχολής Θετικών και Τεχνολογικών Επιστημών έκριναν ομόφωνα τον Frank Leymann, καθηγητή του Πανεπιστημίου της Στουτγκάρδης, άξιο να αναγορευτεί επίτιμος διδάκτορας του Τμήματος Επιστήμης Υπολογιστών της Σχολής Θετικών και Τεχνολογικών Επιστημών του Πανεπιστημίου Κρήτης. Ο κοσμήτορας της Σχολής Θετικών και Τεχνολογικών Επιστημών, Μιχάλης Σταρουδάκης, καθηγητής του Τμήματος Μαθηματικών και Εφαρμοσμένων Μαθηματικών, αναγορεύει δημόσια τον Frank Leymann, επίτιμο διδάκτορα του Τμήματος Επιστήμης Υπολογιστών και του απονέμει όλες τις προνομίες που απορρέουν από το πανεπιστημιακό αυτό αξίωμα, ο κοσμήτορας της Σχολής Θετικών και Τεχνολογικών Επιστημών, Μιχαήλ Ταρουδάκης, καθηγητής του Τμήματος Μαθηματικών και Εφαρμοσμένων Μαθηματικών, ύστερα από ομόφωνη εισήγηση της συνέλευσης του Τμήματος Επιστήμης Υπολογιστών και ομόφωνη απόφαση της Κοσμητείας της Σχολής Θετικών και Τεχνολογικών Επιστημών, απονέμει τον τίτλο του επίτιμου διδάκτορα του Τμήματος Επιστήμης Υπολογιστών της Σχολής Θετικών και Τεχνολογικών Επιστημών του Πανεπιστημίου Κρήτης στο Frank Leymann.
Επίδοση των μεμβρανών από τον πρόεδρο του Τμήματος Φυσικής του Πανεπιστημίου Κρήτης, καθηγητή Ξενοφόδο Ζώου.
So before I start, I would like to express my thanks that this session has been dedicated to my friend Christian Nicolau. Thanks for making it possible. Thank you very much. As I said, it's a big honor to receive this honor, and at the same time, I'm incredibly sad that my friend passed away, but I'm sure that most of you share the same feeling. So the talk that I'm giving today is on the way of gaining insight. Interesting. I hope that works. This is very interesting. So technology strikes back. So the first thing is I would like to remind the paradigms in science that we had for the last 2 millennia. Would like to sketch out what e-science is in the meantime, and would point out what the impact on publications of e-science is, that how we will publish in the future, how we will capture knowledge in the future, and I pass then over to what computer science can also do in the humanities, and then as usual a quick summary. So scientific paradigms. So what did we see? So the paradigms on the scene is the first paradigm was based on experiments. Since a millennium we are used to document experiments in a very rigid manner and the outcome of our experiments and describe the natural phenomena that we are observing. Then a couple of hundreds years ago theory came up based on the advances in mathematics, and we were now able to generalize and create new mathematical models, and here you see a bunch of equation systems that you have here. Then a few decades ago, due to the advancements in computers and compute power, right, the third paradigm appeared on the scene, which is called computation, right, where you simulate mathematical models for equations that cannot be solved in an analytic manner, right, because many of the equations that we have done in theory cannot be solved by mathematical methods, so you have to use numerics for it. And then, about 2 decades ago, we had large instruments out in space, the Hubble telescope, for example, or we are parsing genomes and so on, right? It's the paradigm of data-intensive science, where you have software-based analysis of the data that are produced by these instruments and the simulations when solving otherwise unsolvable mathematical equations. So the fourth paradigm, and its computer science impact has been documented in a book published by Tony Hay, based on a few presentations that Jim Gray gave. Jim Gray is a Turing Award winner for his work on database and transaction systems, and he basically said that the new wave is the fourth paradigm. And then in Stuttgart we basically won what we call here an excellence cluster, so we have about 150 PhDs working in the area of simulation technology that are all contributing to e-science. Right? And we started about 10 years ago, and the US felt that this is a threat to their economy, I'm serious, and they launched another task force where they then reported how important cyber science and cyber engineering is for the US economy, and they are also now investing in simulation technology and that like. So the vision we had is to support the complete process from data acquisition to simulation to analysis of data. So, according to Jim Gray, what you have is you have experiments, instruments, computation, but also literature study, and out of that you get tons of data. And this data then needs to be analyzed and visualized to gain new insights, right? This is very easy. These are the players on the scene. And how do we do that in e-science? Well, in e-science, we don't care about the actual experiments and literature studies, but what we are doing is what is called in silico experiments, right? In silico, because computers are built out of silicon, you do the experiments in the machine, in the computer. And you get data out of instruments and computations, and then, as before, you do the data analysis. And what you see here is you see simple descriptions of what to do. You need to get the data, transform the data, solve your partial differential equations, get the output, transform the data so that visualization algorithms can render it to be understandable for human beings. And what you see here below is a scientific workflow. So what the community mostly agrees to is that scientific workflows are the basis to describe your in silico experiments. Right? And we don't deal into the details of such a workflow, but this workflow need to deal with huge amounts of data. They are often running for a long time, and they need to integrate multiple data sources, especially sensors. And what we are doing here, what we described in this paper, is that you can even use conventional workflow technology that is on the market since 2 or 3 decades to run this in silico experiments. right? Because before that, people built their own workflow systems, they haven't been robust enough, and so on. Then what these workflows, these in silico experiments invoke are, well, we need to invoke the analysis routines. We need to interact with the sensors. So that basically means that we need to extend middleware that is called a service bus. A service bus in computer science is a mechanism that can reach out to each and any kind of code, can reach to any kind of data sources, and it has been built in the business world. And what we needed to do for this e-science is to extend this whole infrastructure to be able to invoke code that scientists have produced, to reach out of data that scientists have had produced and stored somewhere. So, and when you get data from sensors, when you solve partial differential equations, the results that you typically get are not precise. That means the whole infrastructure needs to deal with imprecise data. So we needed to change all the existing infrastructure so that the infrastructure is aware of quality of data. So the in silico experiments, the workflow, need to be able to branch on the quality of the data. We needed to change the existing service bus technology to be able to discover algorithms based on the quality of data that they produce. So we needed to touch everything in existing middleware in order to enable this kind of being aware of different kind of quality of data. Published here with a colleague of mine, Sharon Luster from Vienna in the university, who also was a great friend of Christos. So when scientists would like to make their experiments, but they don't want to cope with huge infrastructure. They even don't want to understand that there is middleware, that there are service buses, workflow systems, and so on. They only want to push a button to set up their experiment, and then the experiment should basically run. So this is what we call bootware. It's a special kind of middleware in computer science that enables you to boot up the overall system, and these days, of course, in the cloud. So what we are doing is, when the scientist wants to start an experiment, this is the in silico experiment that he basically designed, right? Then he wanted to push a button, and then what we call a provisioning engine gets invoked, and this provisioning engine lays out all the required middleware. Typically, you can install it automatically in the cloud. Then the experiment is, so to speak, uploaded and is now run in this just set up environment. When the workflow runs, right, we are reaching out to the services that are running elsewhere, and the services are, again, automatically provisioned, so they don't need to run at any point in time. We only need to have descriptions, and then we basically provision them and set them up. So this is on-demand provisioning, again, described elsewhere. Then a completely new idea came up. It is called multi-scale, multi-field simulation. So since about 10 years ago, people were aware that they could simulate at particular scales, at the macroscopic scale, at the microscopic scale. There were algorithms in chemistry, in biology, in physics, but there was no means to have integration between them. And very often, if you want to simulate, for example, the stability of a skeleton, you need to simulate the stability of each of the individual bones. So you are now in the area of mechanical engineering. They have all of their own simulation algorithms and code out there. But then the stability of the bone is influenced by the stability of the tissue that makes up the bone. Now you are at the sudden in biology, and you need completely different kinds of algorithms to simulate tissues. And the tissue is made up of cells, again, completely different algorithms, because you are now at a completely different scale, in a different field. Have to be there. And what the computer scientists did not solve at this time was, how can you integrate it? Because what they did before is they simulate first the cell, the simulation results then were input to the tissue. If the result was not quality enough, right, they need to run the simulations again. So the idea came up to use choreography technology to do this multi-star, multi-field, multi-physics simulation. That basically means the scientists can now design experiments how to simulate the bone. You do the simulation of the tissues, the simulation of the cells, and now there is business process management technology that allows you to integrate the different workflows called orchestrations into a new thing that is called a choreography. That means workflows that are interacting with each other, called choreographies. And this is what the scientists in Stuttgart are doing. They are modeling choreographies in order to have overall simulations that cover different fields at very, very different scales. Right? And we are not only doing it in medicine, but also in chemistry, in quantum physics, and so on. So this is again described elsewhere. So if we have in silico experiments, experiments that are based on data, solving equations, and visualize stuff, and then you need to analyze the visualized data to gain your insight, well, you have the following problem, right? Because science is about repeatability. That means if the engineers and scientists publish data, they often don't publish the data sources, which then basically means nobody can really repeat the experiments, nobody can really witness whether the result is correct. When we spoke to the engineers and scientists 10 years ago, and I said, you need to publish the data, they were shocked and said, no, I'm a professor. You need to trust me. I never fool around. I said, no, there are people, although they're professors, they are not behaving as they should behave, so you need to publish the data. So this was a shock to them, because the data is their nugget, right? So they didn't want to publish the data, but in the meantime, more and more of the scientists publish the data so that others can get hold of the data and try to visualize the data again and try to repeat the interpretation of the data. And because one data source may depend on other data sources should be linked, because you say, I produce this data, but this input I use this data. So what you at the end need to have is a bunch of open data, and the data are basically linked together into what is called linked open data. And this is very important for repeatability of research according to the fourth paradigm. Right? And what is happening here is the world is creating a web of data, otherwise known as the global data space. Because in the web you have text, images, videos, but if we do science based on computations, right, you also need to publish scientific data. And as I said before, we need to link them to create what is called a data we are moving from a data island to a global data space, and the links for the specialists amongst us are based on RDF. It's a technology in semantic web. Right? And here what you see is a snapshot of the global data space. 1 year ago, each of the bubbles in this graph are databases. Some databases are extremely huge, like DBpedia. Some are small. All the papers and results of Nobel Prize laureates have been published there, and so on. So it's growing and growing. So every year they get published around summertime. Right, you see that the cloud here is getting larger and larger and larger. So the next fight that we basically had is, well, now the engineers and physicists and biologists move towards publishing data, although very, very reluctantly. The next fight I had is, now you publish the data, but I need to get your algorithms. Because you use the algorithms on the data to analyze the data, to visualize the results of the data, and now they were finally really fainting. They're saying, but this is my piece of code, I'm never going to publish it. My argument was, well, the taxpayer paid for it. It belongs to the taxpayer, you need to publish it on the internet. So you need to publish both data as well as the algorithms to allow repeatability in science. Very reluctantly, the people are following it, and this concept is called a compute unit. So we have linked open data, and for each of the data sources, right, in future, this is my bet, you will need to publish also the algorithms that produce the outcome, that produce the results of the data analysis. Because otherwise, again, it's not repeatable, it's not really science, right? And then, if described here, and then after, then you can get to the web. If you want to repeat a certain in silico experiments, you can go to the web, and then use what I mentioned before, a provisioning engine that automatically accesses these algorithms, installs the algorithms wherever you ask the provisioning engine to install it, and then you can analyze the data, repeat the scientific result, and say, yes, this is really true. It's this new insight into science. So this is now the impact on publication. Then the question is, how can we capture knowledge not only in science but also in the humanities? And then we went back and fell in love with a concept called patterns. A pattern is a concept that has been introduced by a real house architect, right? It's called Christopher Alexander in 1977, and it's a technique to document techniques for solving classes of recurring problems in the abstract. So a pattern is a document that describes how to solve a particular problem, but it's not a piece of code. It's not an algorithm that describes step by step how to do it, but it describes it in the abstract. And then you need to re-implement it if you want to build the algorithms in an Amazon cloud or on your Linux machine. You need to implement it by yourself, but the text describes all the main essence of how to solve it. And the main essence is called in this community a nugget of advice. So a pattern is a document, is a nugget of advice, right, to teach you how to solve a recurring problem. And here's one, so one of my famous patterns, a beer hall pattern. So Christopher Alexander has produced a book, it's 2,000 pages thick like a Bible, and he describes hundreds of different patterns, how to solve construction, building problems. And one problem here is a beer hall, and each pattern has a particular name, right? It has a description of the problem in a single sentence. What is the problem? What is the context you very likely run into this problem? And then you describe the forces. Why is the problem difficult to solve? Why should you read the pattern in order to gain some insight? And then comes the more lengthy description of the solution itself. And what you have finally is a little sketch that summarizes, so to speak, the description of the pattern. And the main idea is, once you read the pattern, and after a couple of months or even years, you need to revisit the pattern again, all that you need is you only need to read the sketch, and then you remind all the other stuff. And then the pattern is over, but what we also have is the pattern describes other patterns. It links to other patterns, because the insight of the person who describes the pattern is, if you run into this problem, you very likely also run into that problem and or that problem. So the patterns, in fact, build a web of patterns. It's a graph. At each node you have a pattern, and then each pattern points to other patterns that describes problem and the abstract solutions you very likely also run in. So and this is called a pattern language. Right? It's a directed graph of patterns where each pattern solves a problem and it points to other problem areas you very likely run in if you need to visit this kind of a pattern. So patterns have been widely adopted in computer science. Here's one that my team has basically created. It's a pattern language for cloud computing that is heavily in the meantime used in the industry to move applications to the cloud and inspect whether applications are worth to be moved into clouds. And here you see it's really pattern language. Each icon represents a pattern, and then the patterns are basically linked to each other. So how do you use patterns to solve a very concrete problem? So what you do is you have a very concrete problem. For example, I need to scale my application. And then the pattern, what you do is you determine the pattern advising how to solve the problem. Yeah, you determine the pattern, the concrete pattern that advises you how to solve the problem. Here's a part of a pattern language, and here you basically see, scalability has to do with elastic load balancer, so the pattern language guides to that point. Then you need to determine the context of your problem. So you say, my application is in fact a so-called WAR file that runs in Microsoft's Azure cloud. What you do next is you pass the actual parameters of your problem, namely the fact that it's a WAR file in Azure. You pass that to the pattern language, and then the pattern language steers you to the concrete solution, right? And then you actually get the solution that tells you, okay, in Azure, you deploy WAR files as follows, and then you can follow the instructions and basically do it. This is how you use pattern languages to solve concrete problems, right? In science, we do the very same. If you have a very concrete problem, for example, solving this binomial equation, what you do is you determine first the pattern, that means the formula that describes you how to solve the equation. Then you determine the context. The context in this case are the actual parameters of the equation you need to solve. Then you pass these parameters into the pattern, i.e. the formula, and then you compute the solutions out of it and get here the solutions. So it's the very same mechanism that you use in science if you have a particular problem to solve that you can use with patterns. So this means the hypothesis is pattern languages are similar to formulas. So, and I proved it by analogy, and if you are not convinced, I try to prove it by induction, by showing you other areas where the same methodology can be used. So now we come to digital humanities, right? Because digital humanities can gain a lot by using computer science to get new insight. So what we are doing, also we are dealing with costumes. So why should I, as a computer scientist, deal with costumes? Very strange. My colleague said Frank is now going balloony anyhow. So what we are doing in this project is we take 3 different film genres, and out of each genre we determine a particular corpus, and then we have researchers that are watching movies. And they couldn't believe that I paid them to watch movies, so they sit there and watch movies, they identify the characters, and then they describe the individual clothes that the characters are basically wearing. Because the main question we want to solve is there a costume language? Do we have traditions that movie makers follow in order to express certain effects by means of clothes? So by taking a look at the different clothes, right, we have specialists that then identify which of the clothes have an effect. So costumes are clothes with an effect. And then we have costumes with the same effect. These are then the costume patterns. And we do this by having an ontology. So we have created a huge ontology that the researchers are using to describe their clothes in. So they use the ontology to describe the particular clothes. And clothes consist out of base elements. So if I have a clothing here, right, I have trousers, I have a jacket, and since 10 years I wear a tie. And the base elements, like a jacket, they consist out of primitives. Like a jacket has a sleeve, has a collar, and so on. So this is what we are doing, this is what we are describing at a very, very detail. And next what we did is, in order to bring computer science in, we created a formal language out of it. Right? So we defined a grammar for base element, and the grammar defines, well, a business outfit for male consists out of trousers, out of a jacket, out of a tie, and so on. And the grammar also describes how to compose the word jacket out of the base primitives. That means color, sleeves, and so on. So there are formal languages, and we can solve word problems to find out whether a given costume is really within the tradition. Right? This is the famous word problem that most of you know. Right? Then we have a Boolean function that determines words, that means clothes, that have effect, that means we identify costumes. And then there is an equivalence relation that builds out of costumes equally affecting clothes as the patterns. Right? And then we built 2 systems. One system where you can store patterns. Each and every pattern language is described here. So in mathematical formulas, this is the stuff, the patterns, these the equivalence classes that we store here. And we have solution repositories where you can store the actual clothes. Right? And there's also a bunch of mathematics behind it. Right? So these are systems that we basically built. The systems are described elsewhere here. And then we land back, what are we doing with these movies, right? And being a mathematician, astrophysicist by education, right? What did Tycho Brahe do when at night he was watching the positions of the planets, and he was observing, and then he basically scribbled down his observation. That means he was doing data capturing, right? In very detail, he captured the positions of the planets in the sky. Then, once he did that for many years, another guy stepped up, named Johannes Kepler, who took the data that Tycho Brahe produced and analyzed the data. And at the sudden he found out the Kepler law. The orbit of every planet is an ellipse with the sun in one of the 2 foci. And then, once he got the insight, he analyzed the data, he formalized it, and then you have these mathematical formulas for ellipses and so on. Right? So this is, as we all know, the scientific method. We do observation, data capturing, data analysis, and formalization. Very well known in science. Right? And we applied that also now in movie science in the humanities. We basically say, what is observation? When the scientists watching movies, they are observing interesting stuff. They are observing clothes and getting out of and then they describe the detail of the clothes. That means they are doing data capturing. Here you see a screenshot of the tool that we basically built, right? They do the observation, watching movies, and then they have a tool to capture the detailed data, right? And feed it into the database that we call the Muse repository. Muse sounds very nice. It's a German Mustersuche und Erkennen. It means searching for patterns and recognize patterns. So, and then the movies are in the database. Then we use data mining and OLAP technology to analyze the data, to actually try to find out the patterns. What are close with the same effect, right? So this is what we are currently doing, right? We are observing it, and here's a paper where we describe how to use a SQL Server to analyze the data, and the mining project is currently running. And then we abstract this stuff, we basically formalize it, right? So we use data analysis to recognize patterns, and then we have this pattern language that I wrote out before, so there's even a formalization of this pattern thing. And this is the scientific, so the Muse method in movie science is in fact what the scientists do since many years. So in order to prove that this holds, we started a project recently also with a musicologist. So the musicologist wants to find out whether there are patterns to express particular stuff in music, in classical music. So he wants to express he wants to find out how to express sadness, how to express love, how to express the rising sun in music, right? And he will follow the very same methodology, right? He will observe, he will listen to music with his team. We will build a system for his team to capture the details about the movies. So we already have experience how to analyze this data, and then we are going to formalize it. And the tools that we basically have, are generalizable. So the pattern tools is the very same, because this pattern tool that I sketched before holds in the meantime many different pattern languages. And other teams in Europe, in Vienna for example, they're using also this tool to store their patterns there. And solution repository will also be built now for the musicologist. So it means we have a formalization in the humanities. What we had before is, how do scientists approach a particular problem, right? So they have the problem, they know how to, so the method then is to determine the parameters of the problem, then they use a particular formula, then they get the concrete solution, and the same is true in the humanities. So what we are doing in this movie project is, we describe a problem. We need to build a sheriff in Canada in the 19th century. Here in this trivial case, this is also the context. Then we can go to our pattern repository with the term sheriff. And the sheriff basically points to the abstracted pattern, what in principle is a pattern, and then the other details like, well, it should be in Canada and the century, then we point from the pattern back to the concrete observed costume, and then you get a very well description of the concrete costume. So the hypothesis is that patterns in humanities are in analogy to formulas in science, and when I reported to you that I run into problems with my engineers, with my engineering scientists and the natural scientists to publish data and to publish the algorithms, I'm now in hell with discussing with humanists that they use something like a formula, because their argument is all about emotion and we need to interpret everything individually, but I'm up to fight this to the end, right? They need to use pattern languages to describe and formalize their insight. So, summary. The summary basically was, I tried to remind you that using IT in science and engineering is already well established to gain new insight. I reminded you of the fourth paradigm. Then I sketched out that the IT environment to support the fourth paradigm of insight in natural science and engineering is evolving, and I introduced the central point of in silico experiments. This will have deep impact on what will be considered a good publication, right? Namely, you need to open up the data, you need to open your algorithms so that others can repeat your insight. Finally, I wanted to show you that humanities also require repeatable ways to represent knowledge, so patterns seems to be a promising way. And based on this MUSE project that we are running, right, I wanted to show that the humanities can gain a lot from the scientific method in general. So we try to combine, we move science closer to humanities. So thank you very much for listening.
Ευχαριστούμε πάρα πολύ για την παρουσία σας. Μπορείτε να περάσετε στο μπουφέ στην είσοδο του αμφιθεάτρου.
Thank you. Okay. Thank you.